Good morning, everyone. My name is Coenraad Koegelenberg. This is my third term at Automation Works training facility, and this term we did industrial automation, which I built a filament extruder. Okay. Now, the history of additive manufacturing is that in the 1980s, Dr. Hideo Kodama developed the concept of additive manufacturing in Nagoya, Japan, and filed the first AM patents. Now, moving on to 2015, Adrian Boyer launched the RepRap community project, where he wanted to design a 3D printer that could print its own parts and potentially print even more 3D printers. Now, this made the industry spread like wildfire, with makers all over the world all of a sudden having the ability to now build their own 3D printers and design improvements based upon previous 3D printers. Now, the most common 3D printer you would find is FDM 3D printers, which is fused deposition modeling, which use filament, like a spool you see here. Now, this plastic is commonly sold in 1 kilogram rolls and is considered to be very cheap for personal use, but when adding 3D printing to a business, the cost can actually go up quite much. Filament cost on average cost 300 Rand per roll. Nick, would you say that is an average price for 3D printing filament? Now, if we specify on PLA, it would be 300 Rand per roll. Now, you can factor in courier costs if you order in small batches, but if you order in bulk, then obviously it will be taken out. Now, the risk when when ordering other people's products is that the quality is always uncertain because they manufacture it. So either buying premium filament, you pay a lot more for it, or you would always have a risk of quality, and filament can always go out of stock. Now, filament extruders, industrial filament extruders can sell for the lower price of 290,000 Rand and can easily go up to 5 million Rand. Now, why would you want a filament extruder? Now, PLA resin, the plastic granules you need to make filament, and also master batch, the colorant that you add into your filament, PLA resin costs only 30 Rand per kilogram. Master batch costs 38.34 Rand per kilogram. Now, the master batch to resin ratio is 100 to 1. So with your total mix and your cost of material only would end up to 30.8 Rand. That's only 10% of your average price per roll in material cost. Now, something for filament to be considered usable in 3D printing is that it can either be 3 millimeter or 1.75 millimeters. If we focus on 1.75 millimeters, a standard quality would have a 0.05 millimeter deviation from 1.75, but also premium filament quality will then have a 0.02 millimeter deviation. Just something to consider when manufacturing your own 3D printing filament. Now, let's say in our scenario world that you're an entrepreneur and you build an e-commerce brand, and now you've gained money through scaling your business. Now, after you've scaled your business, you decide that you want to cut costs, so you use the money that you have got from the business and you buy yourself a filament extruder. Now, this filament extruder is extremely expensive, but in the end you have no employees that have enough experience to work on this extruder. This is where I come in. Extruders are expensive to buy, and they're even more expensive if you need to fix them constantly. So my extruder is made to simulate that of industrial extruders. So you can have your employees work on my extruder, gain experience on fixing it and also running it, and you don't then have to pay millions every time the extruder breaks, because it's a cheap fix, and when they gain experience they can work on the real extruder. Now, naturally, my problem statement was to design and build a PLC-controlled extruder that melts plastic through a nozzle to create 3D printing filament. This model will help educate technicians on extruders before they work on the real thing, to help to prevent them breaking any parts because of inexperience. Here are some of my design sketches that I had drawn before I started building. And here are some components that I had 3D modeled while in the designing stage. Here you can see a quality sensor which measures the diameter. There are currently no electronics, so it looks quite dear mekaar. But it measures the diameter with the filament running through this small tube here, and this arm amplifies the imperfections in the filament itself. So a magnetic sensor or Hall effect sensor can actually pick up the imperfections. And this is a puller motor which pulls the filament out of the extruder, and based on if the filament is too large in diameter, the filament puller will start pulling faster, and if it's too small in diameter, then the filament puller will start pulling slower, in order to keep the quality close to 1.75 millimeters. Here's my bill of materials, which is all the products listed that I used, with the total approximated cost at the end going up to 7,000 Rand. Here is the program that I wrote, with using 2 PI controllers for heating, which is proportional and integral controllers that heat slowly using PWM, only heating for a moment and shutting off, with the duty cycle being dependent on what the temperature is and how fast you want to heat it up to temperature. Now, the first PI controller that I used was to slowly heat it up to temperature, to not cause the slow temperature having the heater constantly on and burning the plastic or the nozzle, or burning my components down. And the second PI controller then switches over when it's on temperature, keeping it on temperature more aggressively when the filament is added and the plastic is ran through the nozzle. There can be a quite drop in temperature because of all of the heat transfer into the plastic. So the second PI controller is just there to keep it more aggressively on temperature. This in the end gave me problems. Now, my product structure model, out of my whole model, I have an auger assembly, a filament sensor diameter, and a filament puller. Now, here's my auger assembly, which is a large geared DC motor attached to the auger, and here's my nozzle, which has a hole in it that the hopper is fed into, and also has a heater element attached to the nozzle where heater cartridges are inserted, and through the copper contact is then transferred heat onto the nozzle. Now, my filament puller here is a large geared motor with a free spinning axis and a wheel on the free spinning axis. My geared motor is powering the drive wheel, and so the drive wheel is pulling the filament with the free spinning wheel, just keeping it onto the drive wheel. And in the end, this would be the quality control device that I use to keep my filament onto quality. My filament diameter sensor, you can see, is a casing that press fits into the stand. Here, bearings fit in. These 2 bearings act as rollers that just roll the filament through the assigned hole. This is the arm that I talked about, where a magnet will press fit in, and also an ESP32 press fits in. And in the end, this is what I use to amplify the imperfections in filament. Now, here's my project testing. Here you can see the motor running, plastic is being pushed into the nozzle, and here you can see plastic coming out of the nozzle. And in the end, it extruded plastic for a couple of seconds before part failure happened. So in hindsight, this is actually 7,000 Rand worth of plastic. My success is the 3D printed parts didn't melt while the nozzle was heated, thankfully, but unfortunately, they did give problems afterwards. I worked on a lathe for the first time in my life, which was a very fun thing to do. I programmed an AutoWorks panel and helped install it on site. I fixed the 3D printer that was left broken down at the workshop, which was also something very fun. And now the long list of difficulties. My auger bit was not long enough because the description from the e-commerce that I had bought it from stated that it was 300 millimeters, but the hole drill bit was 300 millimeters instead of the auger bit. So in the end, it was too short. The parts took long to arrive, so my whole building stage was in the end delayed by a week because I was so dependent on the auger before I could start building. The PT100 that I was originally given was actually broken, and it took 2 or 3 days to figure out of debugging. And in the last day, when Nick helped me, we finally got the chance to figure out that it was actually the PT100 that was the problem and replaced it quickly. The PI controllers that I had used caused a lot of confusion when debugging because PI controllers are a sort of complex mathematical equation on their own. And having 2 of them work on a single program is not a very fun thing to have. So I used 3D printed parts as mounting points in my auger, and in the end the 3D printed parts ended up failing because of the material being too weak. So that's what ended up with part failure. So overpressure was also a problem because of the overpressure. The overpressure was induced because my hopper was too big. My hopper then added too much plastic in, and not a lot of plastic came out the nozzle at the end. So in the end, my nozzle actually only started building up more and more pressure the whole time. That's what happened. That's what caused the part failure. Because of the amount of pressure, then the motor started pushing backwards instead of the nozzle started pushing forwards, which was kind of surprising. And in the end, you can see in the video me trying to push the motor forwards again. So it did extrude for a very small time, but in the end, it did break. So now I don't know how to build an actual 3D printing extruder, but I know now how not to build a 3D printing extruder, which I think is more valuable than, in the end than having success straight off the bat. Lessons learned: be specific when planning, because a lot of times when I had finished something, I didn't know what to start on next and needed to do more research before I could start building. Being specific when planning can give you a single plan, which you automatically know if you're on schedule and if you're off schedule, and it can help with it better with completing your project. Human interfaces are important for people to see what the machines are doing. Debugging machines are very, very hard when there are no human interfaces that I discovered, because you need to see what the machine is doing instead of the machine actually telling you, I'm doing this, by the way, which can be confusing sometimes. Second opinions show you things that you might have looked over when designing or building anything. And in the end, this is something that I got a lot of advice on, something that, or a lot of stuff that I have looked over. The riches are in the niches. It's just, I did a business course in this term as well. So being modified or stating that your project is a little bit more specific can help people see that your product holds more value, or yeah. My activity log, this is the amount of time that I spent in this term. Now here you can see theory took a lot of time. Tutorial project didn't take much time because it was quite easy. Design project also took a lot of time, but something interesting is because I did work on a sheep sorter for Automation Works, I did spend a lot more time working for Automation Works next door. Acknowledgements. Thank you for Nick for helping me debug the software, giving design advice and helping me fabricate the nozzle that I needed to build. Thank you Wynand for giving me the opportunity to work on an Automation Works panel and being able to go on site. And also something I forgot to add is thank you for letting me be a presenter at the Buzz Week, which was a very good experience on its own. Thank you for showing me a more logical way to structure my program. So when debugging, I didn't go searching for what I needed to edit. And also thank you for yesterday's helping and for helping me get the little bit of plastic that I do have. And thank you for Brian for holding the nozzle onto my design project. Here are my references that I used, some of the research that I did before starting to design my filament extruder. Here's a poster that I set up where you can have a QR code for my website. Here are my contact details and also my problem statement. And also, thank you for listening. Any feedback and any questions will be very much appreciated.